Hi everyone, I'm Xu Guofu. I'm a PhD student from Stony Brook University, advised by Professor Yifan Zhou. In this video, I'm going to introduce our work, learning based on certain dynamic verification of MMC-HVDC offshore wind systems, which was published in 2024 IEEE General Meeting. Here is the outline, including the background, methodology, and case study. I will first introduce the background. The offshore wind energy is growing rapidly in the renewable energy field, and MMC-HVDC systems play a pivotal role in efficiently integrating this power into existing grids. Currently, the United States has set a national goal to deploy 30 gigawatts of offshore wind energy by 2030. And in New York, there is going to be 9 gigawatts of offshore wind energy by 2035. This map shows the offshore wind projects in New York and New Jersey. You can see the wind lease areas in blue. Major projects like South Fork Wind and Sunrise Wind, and key infrastructure like substations and ports, such as the South Brooklyn Marine Terminal. The dashed lines represent how electricity travels from offshore to the grid, highlighting the region's commitment to renewable energy development. For the HVDC transmission system based on the MMC, it is the most preferred solution to transmit the produced energy to the onshore grid. Since the offshore wind energy relies on natural resources, the system dynamics are persistently disturbed by heterogeneous uncertainties. Moreover, the interconnection and transmission of gigawatt-level offshore wind energy heavily rely on power electronic devices, which deteriorates the system inertia and makes the system even more susceptible to uncertain perturbations. So it becomes critical to analyze the uncertainties and verify the system. Traditionally, one of the most common way is to perform scenario-by-scenario checking. However, we cannot enumerate all possible scenarios by Monte Carlo sampling. So, if the missed trajectories have intersection with the unsafe area, it potentially indicates safety risks. In contrast, reachability analysis conducts set-based verification. You can see from the figure. Through a one-time domain simulation, the set of states that the system can possibly visit can be determined without the need for scenario-by-scenario enumeration. Reachability provides a rigorous framework to predict all possible system behaviors over time, considering uncertainties. For the state space model of the dynamical system, as the upper equation, the reachable set is defined as the union of all possible states that can be reached under uncertain inputs. However, conventional model-driven reachability methods are time-consuming and numerically unstable, making them unsuitable for real-time verification of ultra-fast inverter-dominated dynamics. Therefore, in this research, we will develop a learning-based reachability analysis method for studying the uncertain dynamics of offshore wind systems. After introducing the background, I will specifically introduce the methodologies in this research. As I just mentioned, to conduct reachability analysis of the dynamics of MMC-HVDC offshore wind system, we first build a state space model. The model mainly consists of two parts, the offshore wind power plant part and the MMC-HVDC part. In the offshore wind part, the dynamics of wind turbines, transformers, and cables are modeled. For the MMC-HVDC part, we mainly capture the dynamics and control of the MMC and its interaction with the offshore grid and HVDC link. The right figure. It is a typical offshore wind system that was built in this paper. It consists of two AC grids and two offshore wind grids, which are connected to the 4-terminal HVDC grid through MMC controllers. The uncertainty from the wind energy is modeled as an uncertain current, representing the aggregated power from wind turbine areas.
For the offshore wind power plant part, the upper figure illustrates the energy transmission system of an offshore wind power plant connected to the onshore grid via an MMC-based HVDC system. The system aggregates 600 megawatt wind turbines connected to a grid-following two-level converter, which regulates the AEC output. And the voltage is set up through transformers and transmitted via submarine cables. Finally, the MMC operates in grid forming mode, interfacing with a 320 kilowatt DC link for HVDC transmission. This setup ensures efficient and stable power delivery over long distances. Specifically, you can see the figure on the at the bottom. The two-level converter control system combines an outer DC voltage control loop and an inner grid AC current control loop. Both the DC voltage control and current control use PI controllers to regulate DC link voltage and ensure precise AC grid current regulation. For the MMC-HVDC part, this slide briefly introduces the grid forming control of an MMC-based HVDC system. We follow the article at the bottom. Using the DQ-Darrow transformation introduced in this paper, we formulate voltage dynamics, common mode current dynamics, and grid current dynamics. These dynamics are expressed in a state space framework, where internal MMC variables, such as arm voltages and currents, are transformed into steady-state DQ-Darrow coordinates. For more details, please refer to this article.
After building the state space model of the MMC-HVDC offshore wind grids, we will design the learning-based reachable dynamics analysis method. The target of this learning-based method is to build a data-driven mapping. When the uncertainty and time point are given, the reachable set at the given time can be calculated. In this research, we use ellipsoid to represent the set, which is defined by a center and a positive definite and symmetric shape matrix. As you can see from the figure, the blue set is the ellipsoid, and the red points are the system states. However, there are two challenges. First, learning a shape matrix that changes over time is very difficult, especially for fast dynamics in power systems. Second, there is no guarantee that the neural network will output a positive definite symmetric matrix. So, we decompose the shape matrix over time into consistent shape matrix and distance vector over time, making the training process more stable. And then we decomposed the inverse of the constant shape matrix into the transpose of C times C. C is a non-singular matrix here. So it is more straightforward because outputting such an invertible C matrix for neural network is feasible. With the previous mapping, the next step is to design the loss function and train the neural network. How do we train the neural network to generate appropriate reachable sets? In other words, what's the requirement of a qualified reachable set? Here I give two simple examples to illustrate the two requirements of designing the loss function. First, assume we have a dynamic system, and we know the true trajectories. Here, the blue region is the true reachable sets that represents the system states, all system states that this system can possibly visit. If we calculate the reachable set, like the orange region, we know it's too large. It has intersection with the unsafe area. So we may have some false alerts. That's the first requirement, tightness requirement. And second, again, we know the system trajectories and we know the true reachable set. This system is unsafe because it has some intersection with the unsafe area. However, if we calculate the reachable set as a green region, we may have some missed alerts. That's the second requirement, conservativeness requirement. And referring to an article from UIUC, we define the loss function. The first part of the loss function starts from the definition of the ellipsoid and use an indicator function to judge whether the system state is enclosed by the generated ellipsoid. Once the system state is outside the ellipsoid, it contributes to the loss, which ensures the conservativeness. And next, for the tightness requirement, the target becomes minimizing the ellipsoid. The larger the ellipsoid is, the more it contributes to the loss. And finally, a weight is used to balance the two parts. In this slide, the overall procedure is given. We build the dynamic model from MATLAB, and we generate some data. We do offline training and online implementation. And in this process, we have some real data. And we can use the real data to retrain the model. Here is the diagram. We sample the uncertainty levels from the uncertainty sets and formulate the trajectory pool by simulation. So the dataset is built. By applying our device learning strategy, we can train the neural network. And the well-trained neural network is used for online verification. More importantly, by implement the well-trained neural network and conduct online verification, more real-time data is generated, which can be used for fine-tuning. Finally, case study.
In the next few slides, I will introduce the simulation results. The case studies are performed in a typical offshore wind system, illustrated in the left figure. The system comprises 2 AC grids and 2 offshore wind grids, which are connected to the 4 terminal HVDC grid through MMC controllers. We generate 100 uncertainty sets, and there are 10 random trajectories under each set. The center can deviate from the nominal operating point by a maximum of 20%, and the radius of the uncertainty set is uniformly sampled with an additional 10% uncertainty. For the training, a 4-layer neural network is adopted with 2 fully connected layers and 2 billion layers. And there are 64 neurons in each layer. And each billion layer is positioned before each fully connected layer.
Then we give an observation of reachable set and the trajectories for both slow dynamics and fast dynamics. We can see that the reachable set can enclose trajectories precisely and tightly. Then the 2D visualization of the two states variables is given in the right figure. We can see that the ellipsoid encloses the data point quite well. Finally, we quantitatively evaluate our method. For a testing set, the precision is very high and the volume is small, which means the reachable sets enclose trajectories both precisely and tightly. And then we test the speed. Our method runs almost 1,600 times faster than the time domain simulation, so it can calculate reachable set and conduct verification very fast.
So far, we have further developed this method, making it more adaptive to complex systems and unstable cases, while considering more factors in dynamic systems. The latest method achieves better numerical stability, robustness, and training efficiency. This page lists some important references. If you are interested in our work, please feel free to contact us.
Thank you.